My name is Charlie Wood. I'm the Director of Application Engineering Design at Fast Radius. Today I'm going to talk about how to unlock the full potential of additive applications. Here at Fast Radius, we work with a lot of different types of companies along their journey trying to understand how to use additive to improve the current way of making their products. In this talk, I'll help explain who we are, what we're about, and give a simple guide for how to get the most out of additive manufacturing. So who is Fast Radius? Well, we're the leading provider of additive and on-demand manufacturing solutions, all the way from application discovery to product design and testing to production-grade manufacturing and global fulfillment. We're able to work across the product lifecycle, whether it's finding applications by working closely with companies in the discovery phase, to creating a robust fulfillment strategy that reduces waste and inefficiency. So what does that really look like? Well, it can look like a couple different things. It can look like a one-stop manufacturing innovation solution provider that partners with an electric motorcycle company to find the right manufacturing solutions. That means finding the right process for each part in the BOM on a case-by-case basis and providing one solution that enables agility and speed. It also looks like providing prototyping through full-scale production for a robotics company looking to develop a new product in half the amount of time as before and reducing their risk at launch. It also looks like complete rethinking existing supply chain fulfillment solutions to reduce costs, improve response time, and keep airplanes safe and in the air all around the world. We're exceptionally proud of what we've been doing and building here at Fast Radius. In 2019, we were recognized as a World Economic Forum Lighthouse site, which honors companies and manufacturing firms that are implementing Industry 4.0 technologies. At Fast Radius, we're implementing end-to-end digital thread processes in the latest in technology and automation to create efficiencies and improve outcomes in manufacturing. Today, we support on-demand fulfillment solutions through our virtual warehouse, which enables our customers to reduce waste associated with warehousing and ensure supply is more perfectly matched to the demand when it appears. I'll give some more examples of that later on. So let's transition a little bit away from talking about Fast Radius and really talk about the topic at hand, which is additive applications. When we're talking with companies about where to find the value of additive applications, we see four key archetypes. The first one is make the unmakeable. Second, mass personalization. Third, spare parts and supply chain. And fourth, low volume production. So let's talk about each of these a little bit. So make the unmakeable. I think this is a common example for additive manufacturing. And the example we have here is the Adidas Futurecraft shoes. So creating new geometries that were previously impossible, very high complexity part, maybe high performing parts, or even parts in the case of Adidas that grow their brand halo, something that helps convey the brand in the market. The second one is mass personalization. Another really common use case for additive is instead of creating large SKU segments of maybe 10,000, 100,000 units, creating smaller SKU segments, maybe in the thousands, and going after smaller segments of the market one at a time. I think an extreme case of that is actually single unit customization, where a product is created specifically for a user. The sources of value here is that you can actually create revenue uplifts by segmenting the market and then actually enhancing the customer experience. The third example, which is a really good example in these times, which is spare parts and supply chain. So really what we call just-in-time inventory produced on demand. The value here is reduction in supply chain and logistics costs. So actually waiting for that demand to appear before the part might be made by doing things on demand. And the fourth is low volume production. So maybe where you want to reduce the risk associated with large inventories at product launch, you can create functional parts where the economics really make sense at low volume. This is like accelerated product development where you're creating value, also cutting down your development times, and also lower unit costs in some cases, especially when you're talking about tooling. So now that we understand the archetypes, how do we actually unlock the full potential of additive applications? How do we get the most value from these applications? So we actually see three main keys. The first one is understanding the economics. Second is realize what's possible. And the third is embracing agility. So let's talk about key number one, understand the economics. So the first step to really unlocking the full potential of an application, it really starts with understanding the economics. So additive can create much more value than a simple like-to-like part. And I think that's a big misconception, is that most people, when you look at the surface, making a part through additive, probably like-to-like, might be more expensive. But we actually describe the total value of moving to additive as something called the total value of additive, or TVA for short, which characterizes the value in relation to revenue increases and cost reductions. So when we look at the revenue side, which is the top of this graph, we can create brand awareness with new and revolutionary products through brand halo, which I'd mentioned before with Additive, is a really good example of that. We can also go after more of the market with incremental SKUs and even go to market faster in response to demand. Another category is increased functional improvements in which the customer is willing to pay. For example, a $5 part through additive might increase the performance of a $1,000 system by about 10%. This allows probably the product to be sold, the system to be sold at a premium. So that $5 part, yes, it may have gone from a $1 part to a $5 part, but you're actually increasing the value of the entire system through that particular part. And then there are also cost reductions that are worth noting at the same time. This can be associated with faster times to market, so less cost associated with development. There could be supply chain efficiencies where we don't need parts sitting in a warehouse. And so actually paying for those parts and the capital associated with them, or the cost associated with keeping a warehouse stocked and running, as well as there are some cost reductions associated with sustainability and carbon footprint, where when we look at the differences between additive and subtractive manufacturing, there are cases with additive where you're actually using a lot less material. And so there's a lot less waste associated with that, which actually can reduce your costs. It's really like the reason this comes up as key number one is that in a business, if you're not driving value, it's very hard to get traction. And so it's really important that this is the first place you start when you're looking at applications. Okay, so key number two, realize what's possible. So in some circles of additive, the term complexity for free comes up. And this term helps describe the trade-off between complexity and cost for a given manufacturing process. So in conventional processes, increasing complexity creates cost, where the additive curve is pretty flat. And so a good way to think about this is I have a part with a lot of machine time associated with CNC. I think most engineers understand that the more time that it's going to sit on the mill, the more expensive that part might be. And so you might make trade-offs of your part of saying, I'm not going to add this extra complexity because it may not actually create more value in terms of the product, as well as their kind of competing effects. Whereas with additive, these complexities don't actually add cost. And so this is this blue curve that you can see on the graph, where additive is relatively flat, and there's this trade-off with conventional manufacturing in a cutoff point where this complexity comes for free. In the case of like natural materials, and you see a couple examples here on the screen, complexity is like a function of thousands to millions of years of optimization, where the structures enable efficient transports of fluids or materials that really push the boundaries of toughness. With additive, it's like the first time where there's not a penalty associated with design complexity, and therefore these natural materials can actually be used for inspiration for product concepts. So if you look at things like lattices and these organic structures, or maybe even fluid systems that evenly distribute fluids through a system with minimal pressure losses, these may actually be inspired by things that we see in nature, and it's the first time that we can really probe this area of the design space where it makes sense. And so related to this, if you look in the last 5 years, there's been a lot of advancement in the tool sets available to engineers, where additive manufacturing reduces a lot of the limitations of the traditional manufacturing, like we just talked about, which allows these like organic structures like lattices, which create these new aesthetics, which have the promise of new levels of mechanical efficiencies. The tools are not only built on the physical realization of the design, so it's like the first time that we can really take these type of designs out of the virtual world and bring them into the physical world. But the important thing to note is that the increasing computational power that's accessible to all of us makes these complex designs like easy to manipulate. And so now you have software that can quickly converge on optimum solutions for different areas of the design space where you get things that look like the parts that you see here. And some of these may be more, structured and visual or aesthetically driven. And some of these may be kind of more structurally optimized. There are many different ways to talk about like this family of design: lattices, meshes, grids, or maybe just organic, as I had mentioned before. The complexities of these designs like have intent and purpose and can unlock new levels of performance. So we talk a lot about like the design, but another thing to note is that eventually we have to make these designs out of something. And so it's really important to note a big key has been advancing material sets. So wind back 10 years or more, and for additive manufacturing, there are probably only a few materials available. And really the key variable there was like color. You could get the same part kind of made in a couple different colors. And it was really driven towards like aesthetic models, kind of non-functional. When you look at today, there are materials that range from like flight-ready Ultim materials to these soft elastomer materials that are biocompatible. There are also high-temperature plastics and cyanide ester, which is available through carbon, which is designed for fluidic applications with like really high operating temperatures. Or you could look at like more structural materials like a PA12 glass bead, which is a nylon-based material that has glass particles filled in it to improve the strength and impact resistance of like a real filled composites. And so these advancements in the material sets have a direct impact on the type of applications that engineers have access to. And a really good example of this are the EPU materials and silicone materials through carbon. These specific materials, these soft materials, I think most people are used to the rigid materials, but the soft materials have opened up new dampening and energy dissipation applications by mixing the soft material response with things like lattices, which we just talked about. As more applications are found and adoption gains steam, you can expect these material sets to get better and more diverse over time. The great thing is that this is moving really fast, and we're seeing material announcements every couple of months where there are successive improvements to existing materials, or more of the white space materials that didn't exist yesterday are now being created today to give more design flexibility to engineers as they develop their products. The next ingredient is like the advancement of computational tools or digital tools more broadly. The increasing computational power has enabled two different things. First, large and really complex models can now be run in a reasonable amount of time. And the second one is that there are faster solve times associated with intermediate problems. In these graphs, we show how a design can be optimized parametrically and through probing a design space to find the optimum design. In this case, it's a simplified design with a couple different features in it where we're going after rather aggressive mass savings with negligible change to the stiffness. And by using statistical tools with computational tools, we can probe the design space really quickly. In this particular case, using things like physical samples where we could go to experimental testing relatively fast gave us kind of a relationship to the physical world that was really important for calibrating the model. All of this is really grounded in our ability to access computational power where we can run hundreds of thousands of models in a very short period of time. There are also like more specific computational tools that are available to engineers that are enabled through additive manufacturing. So the first example here is topology optimization, which changes the density of local regions in a part to reduce weight. A good example of this is the Additive Futurecraft 4D. Now, what you see here, what looks like a relatively uniform lattice, but if you were to cut this shoe open, what you would see is that the lattice is functionally very different, in design-wise very different, in different areas of the foot. And so the question is, why is that? Well, we have different pressure profiles on our feet individually, but also in different areas of the feet. So the ball of our feet hit very differently than the front of our feet. And so the structure of the lattice accounts for that. There's another example here on the slide that shows some work we have done where you can use things like topology optimization, which is essentially like optimizing the density of your system to account for loads. In this case, this is an example of like a bike seat where we're putting a pressure load associated with how someone might sit on the seat, and then relating that to the structure that is eventually printed. Topology optimization is usually used to reduce weight. You're usually starting with a solid model and kind of working towards reducing weight. A second tool, which is very similar to that, which is called generative design, which Autodesk has as a part of their Fusion 360 platform. So if topology optimization starts with a solid part and tries to remove material, generative design starts with no part and adds material as it's needed. Both of these schemes use simple structural finite element codes at its core and builds optimization schemes around them. They're just starting from different endpoints. This stacking or hierarchical design of tools helps engineer probe more of the design space and conceptualize embodiments that they're not thought of before. So in this particular case, the engineer is defining areas of red where they know that they can't have a part, probably associated with some neighboring system. Green areas where they know that they need material connections to other parts. And then the software is defining within an open design space where the material needs to be to optimize for weight. And so these functionalities are really powerful for engineers, particularly when you want a really great inspiration for how something might look. And oftentimes there are people who will use these as their final designs. So if you're a design engineer, it's okay, breathe easy. It's not going to replace you anytime soon. These tools are useful, but like other tool sets, they're most useful when they're used to inform the design, not necessarily build it all the way. And what I mean by that is it still takes a designer to get the problem set up properly. It still takes a designer to make sure your part will fit in terms of a system or assembly. And it will still take a design engineer to make sure the part meets all the requirements and testing. And so this is like a very complementary tool within the toolbox for engineers. And so the interesting thing is that these lattices and structures, they have like a new aesthetic and kind of a new product semantics that customers are not familiar with just yet. The parts are alluring because they look so different. They're almost radical in the way they look because they challenge what we think we know about how to design a part. This actually provides a great opportunity for consumers to have different experiences with their products unlike they have before. In some of these images with varying lattices, the variation is specifically designed for performance and efficiency, but also has almost like an artistic look to it. Like that is intentional too. And so it's challenged the way that we might design products in some aspects, but it's also can be part of a holistic design approach where the consumer experience sits at the center of the design, where it's about function and look all at the same time. And so computational tools and optimized designs don't always look like complex structures. It can also be radical in its simplicity. So Arevo is a manufacturer of 3D printers that are essentially, you can think of them like FDM print nozzles on 5-axis robots. The process, which is fairly similar to metal DED, extrudes a plastic with a continuous carbon fiber throughout it. So this process allows for direct manufacturing of really complex shapes, but also specific orientations of fibers to the loading direction. So it means that you can create incredible efficiencies that you couldn't get before just through laying up composites. The process is a combination of manufacturing capability, but also getting the design right in terms of the frame and how you might orient the fibers. So it's not only about what it looks like, but also when you look at the frame, the fibers are oriented in very specific ways to be very efficient. So it's a really complex design space when you think about it. It's actually quite large. which could require very large computational models to get it right. In the case of Arevo, the result is a bike that weighs only slightly more than the water bottle used to rehydrate the person riding it, which is pretty amazing. In this particular application, the weight savings actually enables new functionality where there are longer ranges for the electric motor and and basically enables like a new way of transportation that many people before considered quite limited. The last thing here to realize is that parts are not always in a finished state coming off the printer or out of the manufacturing process. Post-processing and cosmetics have come a long way to extend the use of parts from additive technologies. In this case, some of these examples are painted or plated samples, where plating can be used to give a specific look, or it could be used to get rather specific wear, electrical, or thermal properties, so functional properties. Over time, people have learned how to secondarily post-process these materials, as they have with conventional processes, to extend into different industries, whether it be for electrical connectors or for like luxury consumer goods. So the last key here is embracing agility. Some people might be confused about why we're talking about agile product development when we're here talking about making physical parts and manufacturing. These terms are usually not synonymous with each other. And so agile product development has been particularly popular in the software world because engineers can deploy new products almost every day with new revisions and new releases. This means that they first focus on MVP and then incrementally update and change as needed. Where getting that first MVP out is like really important to hearing back from your customers how they're using the product. With additive manufacturing, we can make new parts every week, every day, or maybe even every hour. So we can adopt some of these principles to help us work more efficiently. We describe 3 different principles when we talk about agile product development. There's adapt, prototype, and sustain. The end goal is to be adaptable to change, to try to get functional hardware quickly, and to make sure we can sustain our pace of work for as much as possible. If we drill deeper into how we might evolve a development process, we could look into an agile development digital world as a way of working with physical product development. So we can adapt and allow constraints and conditions to change over time. We can prototype digitally and physically faster than before, and we can sustain production quality while looking at ways to accelerate production. What this looks like in practice can vary, and agile processes are not the solution in every case. In the case of Fast Radius, we use this as a tool in our arsenal that we can use for the right process, where in particular speed is important. So when customers want to get to market as fast as possible, and we can work very closely with them to give that feedback of their products. So shifting a little bit, this is probably a fairly familiar slide to the audience, where it's really a traditional product development cycle where you start with defining your problem, going to design, maybe some simulation, manufacturing, and then testing. In this framing, simulation has always been, or I should say in the last couple decades, has been available to help improve your designs and preview the risk of the part before tooling. So I may have a very weighty decision about whether I want to go to manufacturing to cut steel in the case of injection molding. And so simulation can provide pretty quick feedback about how we expect that part to behave. With additive manufacturing, it actually provides a second feedback loop. So if the first feedback loop is simulation, that we can feedback to the design. Additive, we have a physical feedback loop with prototyping that we can use. So instead of weeks, we can get parts back in days. This is pretty powerful for design projects where now with simulation and additive, I can sample from the virtual and physical world as I design. This not only allows me to reduce time and capital costs, but also helps me get better designs. And so this is what that looks like. If I'm able to use simulation in prototyping, this is an example of us working with a customer where we had sprints defined, where we could spin up and down on prototyping and simulation. The interesting thing here is that we had this like big gap of 12 weeks in red. which doesn't look very great, but it did highlight something that was really important to us, and that was we moved pretty fast. We kicked off our project, and in the first month, we proved feasibility. And it was actually so fast that the business was not ready for that to happen. And so it took a little time to get the right stakeholders aligned to move the project forward. And so that's an important call out of like agile product development, is to make sure that all the stakeholders are involved from the beginning to ensure that you can really take advantage of the velocity that you're driving. Subsequently, after that delay, work continued, and you could see that there was honing in the design where we went to actually more virtual models. We explored more of the design space to get more certainty about where we were, and then begin to dial in our design through more testing and supporting simulation work. So putting it all together. So we have these 3 keys. What does this look like when you put all of it together? So here are a series of case studies that highlight some of these points. So the first case study are the COVID diagnostic swabs. So back in March, if everybody can rewind to many months ago, there was a shortage of swabs that was identified as a critical item in the supply chain as testing was starting to ramp up. Traditional swabs for testing primarily came from 2 places in the world and had very long lead times associated with them. It was a supply chain that was not set up to move very quickly. And so Carbon and Resolution Medical partnered together to design and test a new swab design in less than 6 weeks. So using additive manufacturing, driving incredible velocity in development by listening and watching for an opportunity that posed itself as a shortage in the market. So this extremely short time to market was enabled through an agile development process with daily manufacturing runs to send samples to testing, get approval, and eventually dial in the production process. The end result has been a design that early tests suggest perform almost as well as traditional swabs and might lead to less false negatives. We're extremely happy to partner with Carbon and Resolution to manufacture these swabs and help address some of that shortage. And so it will be, this is a continued thing where these swab designs can change relatively rapidly to new tests that may be developed or maybe new requirements that may come in from regulators. The next example is a little bit different, but related in terms of COVID. So again, back in the early days of COVID, masks were in short supply and people were looking for really innovative solutions to help provide protection. And so I remember back in March and April when it was hard or nearly impossible to go to the store or to order online protective equipment. And so in a relatively short period of time, the Fast Radius engineering team was able to design and iterate over a dozen different designs of this mask, which was targeted specifically for at-home printing. So thousands of companies, big and small, have contributed to this effort, where around the world people have shared designs, lessons, and sources, and we're proud to be part of that. So open source innovation and decentralized production, where people can make these masks at home, was kind of the play here, where there's digital sharing of design information and manufacturing information that made that possible. So not a real manufacturing solution, but a win in terms of the design where people were able to move relatively quickly. So there's been this like global effort to create design repositories where there's this new idea of how do we respond to future crises or supply shortages. The World Economic Forum, National Institute of Health, and the World Health Organization, amongst many others, looking at these problems. The next example is non-COVID related, but important to Fast Radius, which is natively manufactured armrest for a high-end office chair. So a couple years ago, working with Steelcase to redesign an armrest to high-end chair, where the design intent behind the armrest was to create a structure that would mimic the sensation of resting your elbows on your thighs and getting that right pressure profile. So instead of using an assembly of 10 plus components with several layers of foam to get that feeling. This is actually a single piece that is printed all together as one with several different design components, which you can see in the blown up CAD image here, that's integrated into a unified design, which reduces time, cost, and complexity of the final system. The particular design also utilized an agile sprint construct, with the design being developed over an 8-week period with over 100 concepts, 12 printed designs over that short period of time. In the end, the armrest was displayed at NeoCon in 2018, which is like a large interior design convention in Chicago, and was displayed on one of their high-end office chairs. The design was viewed by over 60,000 people and actually won an innovation award at the conference. So a really good example of rapidly developing a product by using complexity of design to create kind of an elegant solution to an assembly. Kind of coming back to another COVID-related application, and a recent one for us, is our development in the face shield market. So rather quickly, back in the spring, we're able to adjust our internal production and develop our own face shield halo. This product incorporates a halo that is additively manufactured, as well as a couple other components purchased off the shelf. The solutions only took days to ramp, with development concentrated over a short period of time, where it took only days to ramp production instead of weeks for conventional processes. So far, we sold over 100,000 shields and responding to that growing demand. We've also used that work to spark other collaborative projects where we develop products to solve like very explicit problems like loops for dentists. Although most of the production is shifted to mass manufacturing processes over a period of time, like to injection molding as the demand has gotten really high. Additive, which used to develop the product and really create a bridge to revealing those larger demands. So it was really important to us in terms of how fast we were able to respond and how we were able to build up to the larger volumes. Another example of low volume production has been our work with Bastian Solutions, which is a robotics division of Toyota. This robot was developed with warehousing in mind. So a picker robot that could grab a very wide variety of objects. So think like an Amazon fulfillment type center where parts need to go into boxes and be shipped out. A key to the success was the short development cycles and very low volume production. Those factors allowed Bastian to enter the market faster with less inventory risks than their competitors. What's interesting is that Bastian started with just a single part. Came to us with this elbow that was made conventionally through CNC and wanted to convert it to additive simply due to the lead times. So 12-week lead times were very difficult for them. It was the gating item in terms of their project, and they could see that they could get to market faster by bringing in that particular item. So they started with that one. They were able to consolidate 6 different parts into one. And then over the life of the program, which was still relatively short, they saw more opportunities, which resulted in a final BOM, which was over 50% additive. So a really great example of starting at one place and kind of seeing how it catches. And they were able to see a lot of value on this particular project. The last example I want to talk about is our work with Sauter. So Sauter provides the ground support for Airbus aircrafts around the world. We often think about the parts that actually fly when we think about the aerospace industry, but there are a lot of parts that are critical to operation that never leave the ground. These support equipment parts need to be on site and ready for use when they're needed, but oftentimes are only in quantities of 1 to 2 at a time. They're highly customized parts that are difficult to source in inventory. Therefore, they worked with us to convert some of those to additive. This has significantly reduced their lead time from weeks to days, as well as reduced the safety stock of the tools. As an added benefit, we're able to customize the aesthetics of the parts to improve their use. You can see some of the examples here on the screen, whether it's embedded labeling, QR codes for specific call-outs of operational processes or part numbers, or even guides to ensure the part is being used correctly. This initiative with Sauter has been part of a larger partnership where we continually find new ways to find the full potential of additive applications. With that, I'd like to thank you for your time. I appreciate the opportunity to be able to talk at this conference. My information is on the screen. If you'd like to continue the conversation, please visit fastradius.com. We have a wealth of information and resources there to help you on your journey.